Okay, so second half of this recitation is really about the chemistry of these species. So even though we talked about a lot of different functional groups, in actuality, their chemistry is really very easy. We study them together because their chemistry is interlinked. So all of the functional groups that we've talked about can be approximated by this generic structure of a RCO double bond connected to some type of leaving group. Every leaving group does the same thing. This connects from the molecule, taking with it its two bound electrons. So your acid halide, your anhydride, your ester, your amide can all be thought of as being structurally similar in that they are a CO double bond connected to a leaving group. But you also know that leaving groups can be substituted by nucleophiles. So we have this recurring theme. And that is one, at least in theory, any of these carboxylic acid derivatives can then be converted into any of the other carboxylic acid derivatives just by a nucleophilic substitution. So you can convert acid chlorides into esters by just using an alcohol. This fits our general description because you could recognize this, for example, as an amide reacting with water to produce carboxylic acid. So these carboxylic acid derivatives can all be interconverted by this type of nucleophilic substitution process. Different nucleophiles, different leaving groups, and that then allows you to interconvert all of those different species. Theoretically, that's at least correct. Conceptually, that is accurate. So this process is given a particular name. So this is nucleophilic acyl substitution. So you know about nucleophilic substitution like SN1 or SN2 or nucleophilic aromatic substitution. This is the acyl version. So the term acyl means, as you know, occurring at the CO double bond. That is the acyl group. So this is nucleophilic acyl substitution. And this allows you to convert any of the carboxylic acid derivatives into any of the other carboxylic acid derivatives or into a carboxylic acid. So all of the chemistry of those functional groups, they are interrelated. So that's the first aspect, how they can all be interconverted using nucleophilic acyl substitution. So we then have the next issue. And the next issue is an issue of relative reactivity. So you have to remember that our general idea is that these are all of the form RCO double bond connected to some type of leaving group. So if we then draw it in this type of way, hopefully you can see that there is then the similarity. Right? All of those species have an RCO double bond connected to something else, but that something else can just be described as a leaving group. So yes, there are multiple different functional groups, but they're all connected in that they are all structurally identical. RCO double bond connected to some type of leaving group. So that's the first thing that links them together. And as you know, leaving groups can be displaced by nucleophiles. But not all leaving groups have the same leaving group ability. So the next issue that we have to address is not really an issue of reactivity, but it's an issue of relative reactivity. All of those leaving groups can be displaced, but some are more easily displaced than others. And you will see these functional groups almost always written in this sequence. And this is their reactivity series. It indicates their relative reactivity. So this way, is up is increasing reactivity. So acid chloride is more reactive than anhydride, but anhydride is more reactive than ester, ester more reactive than amide, amide more reactive than carboxylic acid. And this is reactivity with respect to nucleophilic acyl substitution. They all do it, but it's an issue of relative reactivity. These are more reactive, these are least reactive. So this then brings up 2 points. The first is, how do we explain that? So the relative reactivity is explained by primarily by two different things. So the first is leaving group ability, and the second impact is resonance. So these are the two main features that account for this reactivity series. So the first feature is the leaving group ability. So if I had said to you, for example, we have negative charge on oxygen, which is what we would get if the ester behaves as a leaving group, and we have negative charge on oxygen, but with the benefit of resonance. So of these two anions, which do you think is more stable? Answers in chat, left or right? Which one is more stable? So did people hear that question? Which anion is more stable, left or right? Okay, so this one is more stable because of resonance. That was the whole point, for example, of why carboxylic acids are more acidic than alcohols. So this is more stable than that. This is a better leaving group than that. So anhydride's more reactive than esters. And you can apply that same logic to all of these leaving groups. Negative charge on oxygen is better than negative charge on nitrogen. So esters more reactive than amides. Negative charge on halogens, great because they're so strongly electronegative. So the reactivity series makes sense because we understand what makes these substituents a better or worse leaving group. Because when the leaving group is displaced, it comes off as Lg minus. So better leaving groups are in the ones that are more reactive. Worse leaving groups are in the ones that are less reactive. That's a good way of making sense of that relative reactivity series. The other thing that plays a role is the amount of resonance. So all of these atoms have lone pairs, and therefore have some resonance stabilization. And that resonance stabilization is lost during the mechanism of the nucleophilic acyl substitution process. So kind of like we saw with base strength, anytime that lone pair is stabilized through resonance, it gives you a decrease in reactivity. It's nice and happy when it has resonance and it doesn't want to lose that resonance. So that resonance is stronger here, but weaker as you go up. So the functional groups lower down have more resonance, therefore more stable, therefore they are less reactive. The ones higher up have less resonance and therefore don't mind reacting. So this again helps us make sense of this reactivity series. Now this reactivity series is important because it dictates which reactions are easy and which reactions are difficult. And the way that I describe this is we are looking for a downhill reaction. Downhill reactions are favorable when you go from a more reactive species down to a less reactive species. So you can think of this just from like a thermodynamic standpoint. You want your reaction to be exothermic, right? So you want to go from high energy to low energy. You want to convert reactive things into stable things. This is our reactivity or stability series, and these downhill reactions are easy. These downhill reactions are favorable. And so what that means is just by adding an appropriate nucleophile, you can convert if the reaction goes downhill. So a specific example would be if you want to go from anhydride to amide, all you have to do is add the appropriate nucleophile, and that reaction works. Or if you wanted to go from acid chloride to ester, just add the appropriate nucleophile. And all of these downhill reactions work. So downhill reactions favorable, just add the appropriate nucleophile and you convert something more reactive into something less reactive. What's more challenging is to do an uphill conversion. And in general, what we would say is that these uphill reactions cannot be performed successfully. You must say, but you just said all of these can be interconverted. They can, but the downhill conversions can be done directly. The uphill reactions cannot be done directly. They have to be done incorrectly. And to do that, we need to convert our carboxylic acids into an acid chloride. And we do that using thionyl chloride. So thionyl chloride, as we learned in our aldehydes and ketones chapter and in our carboxylic acid chapter and using again here, will convert carboxylic acid to acid chloride. So if you want to go from, let's say, amide to anhydride, formally that's uphill. You cannot do it directly, but you could go amide to carboxylic acid to acid chloride to anhydride. So you're exploiting always going down, but you can go from the bottom back up to the top using your thionyl chloride. So downhill is easy. All of these downhill reactions are favorable. But if you want to do an uphill reaction, the best way is to do down to carboxylic acid, thionyl chloride up to the top, and then downhill from your acid chloride. So you can interconvert all of these. Downhill, you can do it directly. Uphill, you have to do it indirectly. So this relative reactivity of downhill being favorable, there is one other aspect to that. And that is, if you do these reactions and let them go to equilibrium, the downhill reactions will always give you more product than starting material. But if you have an equilibrium process, you can have a reaction that can give a small amount of product. So if you were talking about amide to ester, if you add an alcohol to amide, it's not all going to convert it into ester because that would be uphill. But a small fraction of that would give product. So what we can do is if you can establish an equilibrium and then manipulate that equilibrium, so this is taking advantage of Le Chatelier's principle, if you set up an equilibrium and then impact that equilibrium, for example, removing the product once it's formed, your system will respond to make more of that product. So downhill reactions are favorable, giving you more product than start material at equilibrium. But some, you can sort of do these slightly uphill reactions under forcing conditions, for example, using acid, and then manipulating your equilibrium. So you would know you can convert carboxylic acid to ester, but you have to do that through an equilibrium and then manipulate that equilibrium, maybe continuously distill your ester or some other way of manipulating or impacting that equilibrium. So really the important message is downhill always gives you more product than starter material. Easy to do. If you want to go uphill, you can either just go all the way to the bottom, back up, and then down the appropriate amount using thionyl chloride at the carboxylic acid stage. Or if your functional groups are pretty close and you can set up an equilibrium, you can then manipulate your equilibrium. So remember that at equilibrium, an uphill reaction is not going to give you more product than starter material. It's going to be mainly starter material. But if you want to manipulate your equilibrium from a practical point of view, you are able to then get to a meaningful amount of product. So that's really an explanation of the relative reactivity. There is one other topic that we need to address, But does anybody have any questions on relative reactivity and uphill or downhill reactions? If you have no questions, type OK. Okay, some people still awake. So the last section has to do with the mechanism of these transformations. So overall, our transformation between one carboxylic acid derivative and the other is just the interaction of a nucleophile substituting for a leaving group, giving you the product where substitution has occurred, and the leaving group has obviously been displaced. So this is a substitution, it's a nucleophilic substitution, but it's a substitution occurring at an acyl group. So this is nucleophilic acyl substitution. Now, the most important thing to notice or be aware of is that a nucleophilic acyl substitution is different to an SN2. It's very tempting to say, well, this just substitutes here, kicks out its leaving group, gets me to the product. That's not the mechanism. The mechanism is an example of a two-step process that's called an addition-elimination mechanism. So the first thing that happens is the nucleophile attacks the carbon of the CO double bond. It does so because of the polarity of that carbon. You would know from your chapter 18, aldehydes and ketones, the carbon of a CO double bond is polarized such that the carbon is positive. The leaving group will also make that carbon even more positive, so it should be totally unsurprising that the nucleophile goes for the carbon in your carboxylic acid derivative. But the key to understanding this mechanism comes from the answer to the following question. In this molecule, what is the weakest covalent bond? I will accept your answers in chat. Tell me what is the weakest covalent bond in our starter material. Which one is it? I don't see any correct answers yet in chat. So you've got to think about the correct question. So if I'd asked the question another way, everybody would have got it correct. And if I said to you, which bond is stronger, a sigma bond or a pi bond, what would you correctly answer? Sigma or pi? Right, so sigma bonds are stronger than pi bonds. Another way of saying that is pi bonds are weaker than sigma bonds. So when your nucleophile attacks this carbon, it sees sigma bond, sigma bond, sigma bond, and pi bond. So the weakest bond, the two electrons that are most easily displaced from this, are the pi electrons. So when our nucleophile attacks, these 2 electrons in push out the pi electrons onto the oxygen. You might say, well, why doesn't the leaving group come off? I would say, but the leaving group's connected by a sigma bond. Pi bond is weaker than sigma bond. That gets you to this type of intermediate. That type of intermediate has a special name. It is called a tetrahedral intermediate. And it's called a tetrahedral intermediate because of that carbon. That carbon is sp3 hybridized, which means it's tetrahedral. And you might say, organic chemistry is full of sp3 hybridized carbons. Why, in the last recitation of the last semester, why are we calling this thing tetrahedral? And we're calling it tetrahedral because notice that this carbon is not tetrahedral in the starting material. This carbon is sp2, therefore trigonal planar. This carbon in the product is also sp2 hybridized, trigonal planar. But the intermediate through which this reaction proceeds, the carbon is sp3. So there is a change in hybridization of this relevant carbon. It goes sp2 to sp3 and will eventually go back to sp2. But it proceeds through a tetrahedral intermediate. We form the intermediate as we showed there. Then, Then, to get to our product, all we need to do is reform our CO double bond and then expel our leaving group. So notice, this is a 2-step process. Nucleophile attacks, nucleophile adds, forms tetrahedral intermediate. Second step, reform our CO double bond and the leaving group is expelled. 2-step process, addition, elimination mechanism. This overall action of addition and elimination achieves substitution. It's substitution of an acyl carbon by a nucleophile. The most important thing to remember about nucleophilic acyl substitution is what it is not. What you cannot do is say nucleophile comes in, leaving group departs, gets me straight to my product. You might say gets me straight to my product. My answer is simpler than yours. This bond doesn't break before this one. That mechanism only works if sigma bonds are weaker than pi bonds. And we know that that's not true. So that cannot happen. You might think it would be simpler, it should happen, but the bond strength dictate which bonds get broken. So nucleophilic acyl substitution must proceed through a tetrahedral intermediate. It's substitution by a nucleophile at an acyl carbon, and it's a multi-step process, addition of your nucleophile, producing a tetrahedral intermediate, then in a separate step, reforming of our CO double bond, which is accompanied by expulsion of the leaving group. Here I've written the simpler version, which is the base catalyzed version. In the notes, there is also an acid catalyzed version. Just like nucleophilic addition had acid and base versions of mechanism, nucleophilic acyl substitution also has those acid and base versions. So anybody have any question or issues about the mechanism for nucleophilic acyl substitution. It's basically one mechanism works for all the reactions in this chapter. It's just different leaving groups and different nucleophiles. So if you have no issues with that mechanism, type no in the chat. Okay, so today we talked about what makes a carboxylic acid derivative, has to fit a certain definition. Then we talked about the IUPAC naming of those different species, plus 2 cyclic versions. Then we talked about their reactivity, which is nucleophilic acyl substitution. Then we talked about their relative reactivity. So lots of functional groups, lots of interconversions, but really one main mechanistic pathway. So I would say that's really all you need to know to make sense of chapter 21. So we did an hour and then we've just done another half hour. I think that's a pretty good summary of chapter 21. Does anybody have any topics or specific questions they would like answered? If you don't have any specific questions, then I would say that this then recitation is complete. So if you're ready for it to be done, if you type bye in the chat, I'll know that everyone is satisfied and you can then start thinking about getting ready for exam 3. So I will accept either thank you or bye as an indication that you're ready for this to be over. Okay, if that's the case, then I will say it was nice to talk to you, and maybe sometime we may actually get to see each other in person. So, all right, everyone stay safe and healthy. I'll see you next time.